Okay, so we're going to start with method of cylindrical shells. So we did area between two curves, and then we did washer disk method, and now we're going to do method of cylindrical shells. So this is going to start in your note packet, and then we're going to pick up with that extra note packet that I always give you, and that is in the file, the PDF file that is attached in Google Classroom. And then this part without the video will also be posted, like the answer key, if you want to call it that, will be posted. So you're going to need your note packet very briefly. You may not even want to pull it out. And then you're definitely going to need the packet printed, okay, which is also available on the printed materials, because we will take notes and do examples in that packet. Okay, so washer disk method. The difference in washer disk and cylindrical shell is washer disk, we were literally, our slices that we were taking. So when we did area, we had these rectangular slices. So if you go all the way back to Raymond Sums, when we did area, we just had a two-dimensional rectangle. And then we learned how to do those infinite ones with the integral. So it was just these infinite rectangles. Then we did washer disk. So then we had a three-dimensional shape because it was volume, and it was either a washer or a disk. Okay, so it was a circular, either a complete solid or a semi-solid with the hole in the middle, right? That circular hole in the middle. So cylindrical shell makes a cylinder. So if you'll look right here at figure 2, you get a cylinder when you make the area. So your slices are now like infinite, like soup cans. So if you can imagine a soup can without the top and without the bottom, that's what your slices look like. Okay, so you have these infinitely different size soup cans that kind of fit inside each other and make up your solid. Okay, so whereas, again, area between curves was a two-dimensional, because area is two-dimensional, rectangle, infinite rectangles. Then we moved on to washer disk. So then our slices were infinite discs, solids, like a quarter, or infinite washers, like a washer, so a solid, a semi-solid with the hole in the middle. Now our slices are infinite cylinders, okay, like an empty soup can. So what that means for us is you have a new formula. This 2 pi r times the height times the thickness. And what that means is your circumference, 2 pi r, and then your height, and then your thickness. So it gives you, you can see these infinite cylinders here as they change size. But this is the packet, okay? So it goes through some examples in the notes, but I think we have all agreed up to this point that it's much more useful to do these little packets together, okay? So if you can't determine volume with a disc or a washer, we can do cylindrical shell method. Now, in every class that I've ever seen, they've broke this apart for you, so you don't have to choose which one to do. You may, if you take like honors calculus, they may have you choose, you just give you volume, and you have to decide whether it's washer, disk, or cylindrical shell. But in most of the classes I've seen, they're like, determine if this is washer or disk, and then you use method of cylindrical shell, like they break it apart for you. Okay, so we have that volume is equal to 2 pi r times the height times the thickness. So circumference, 2 pi r, which is circumference, the height, and the thickness, okay, which is 2 pi r h dx if it's in terms of x. So if we rotate about the y-axis, the volume will be in terms of x, okay? So if we're rotating around a vertical line, then your formula should be in terms of x, where x is the thickness, the function is your radius, or your height, and then, of course, dx, the delta x is your thickness, the change in x, right? Okay, so obviously they don't state this, but if we're rotating around a horizontal line, then this would all be in terms of y, okay? So let's look at example 1. So it says, use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the given curves about the y-axis. So I know if I'm going about the y-axis, then this should be delta x. Okay, so we have y is 0 and x is 1, so that's first quadrant. So if y is 0, then this is going to go through 0, 0. If x is 1, it's going to go through 1, 1. So I'm going to do 1, 1 like that. So y is 0 is here. X is 1 is here. And then y is equal to x cubed. So I know if it goes through 0, it's 0, 0. And it goes through 1, 1. Remember, cubic is that little snake, so it comes up. Looks like this, sort of. Okay, so if we're talking about the area bound by these curves, that's here. That should have been a little curvier, but it is what it is. And we are going to rotate about the y-axis, so this direction. Okay, so again, that means that my thickness runs this way. So these, when I rotate around, I'm going to get these infinite cylindrical shells, right? These infinite empty soup cans. Okay, so that means delta x. So delta x. So volume is equal to, and I'm going to bring my 2 pi outside because remember, that's a constant. I'm not going to make it any more difficult on myself than I have to. So this one, you can't really mess the bounds up because they're the same either direction you go. But remember that if we're integrating in terms of x, our bounds have to be in terms of x. So that's 0 to 1. 0 to 1. Okay, so remember it's 2 pi RH delta x, right? Okay, so 2 pi. So my radius is my x value. So from here to here is my radius. So whatever that x value is, whatever that x distance is from 0, that's my radius. My height is to this function. So this from here, from the x equals 0, y equals 0 to the function, this distance is my height. So this is r, this is h, right, of my cylinder, my soup can. So that would be the cube root of x. And then delta x becomes dx. So we have 2 pi, 0 to 1. Now we know this is x to the 1/3. Product rule says when we multiply two like bases, we add their exponents. So that'd be x to the 4/3 dx. So we have 2 pi. Add 1, so 7/3 over 7/3. Evaluate it from 0 to 1. So I have 2 pi. I would probably go ahead and bring out my 3/7, so that would be 6 pi over 7. 3 times 2, pi, right? Multiply by the reciprocal of x to the 7/3 evaluated from 0 to 1. So of course that's going to be 1 minus 0, which is just going to give me 6 pi over 7. Okay? Now remember, if I move too fast through, just pause the video so that you can finish copying if you need to. Okay? Alright, so method of cylindrical shells, rotating by the given curves about the y-axis. So again, if I know I'm rotating about y-axis, it should be delta x. So we probably need to figure out where these intersect. It may not just be the first quadrant, but we need to figure that out. So I'm going to do x squared is equal to 6x minus 2x squared. So personally, I like to keep my squared term positive. So I'm probably just going to move everything to the left, which is a little more work, but I'm just going to. So if I add 2x, that gives me 3x squared minus 6x equals 0. So then I'm going to factor 3x, x minus 2. So x is 0 and x is 2. So they do intersect in the first quadrant. So 1, 2, And I'm going to go ahead and make a t-chart so I have an idea of how big my graph needs to be. So 0, 2, so 0, 4, so 1, 2, 3, 4. Obviously the other one's going to be the same way. So let's graph x squared. We know is a parabola, so it goes through 0, 0, and 2, 4. So it looks like this. And the second one is a downturn parabola that is also going to go through 0, 0, and 2, 4. I probably need to find out a point here to kind of get where I'm going. So I'm going to see where it's at 1, just to kind of get an idea of where I'm going. So 6 minus 2 is 4. So the peak happens somewhere between that. 1, oops, sorry. 1, oh my gosh. There we go. And so we're going to have a nice little parabola that comes back down like that. Okay, but the only area we're concerned with is here, and we are rotating about the y-axis. So remember, that means that this is the outline of my shell. Okay, so this distance is r, and then this distance is height. Okay? Alright, so volume is equal to 2 pi. So remember, first of all, that our bounds have to be in terms of x because I'm integrating with respect to x. So that's going to be 0 to 2. So it's 2 pi r h delta x or dx. So my distance here is x. This is left to right. So whatever this x value is, that's my radius. So I have radius. Now my height is the distance between these two functions. So it's kind of reminiscent of finding the area between the two functions. How do I find the distance between those two functions? You subtract them, right? So what function is on top? Well, the red function. So that's 6x minus 2x squared minus the blue function, which is x squared, and then dx, my delta x. So I have 2 pi, 0 to 2, x times, so negative 3x squared plus 6x dx. So 2 pi, 0 to 2. Distribute my x, so negative 3x cubed plus 6x squared dx. So 2 pi, negative 3x to the 4th over 4 plus 2x cubed. So that would be 6x to the 3rd divided by 3. And I'm running out of room, so 6 divided by 3 is 2. Evaluated from 0 to 2. So 2 pi, negative 3, 2 to the 4th over 4 plus 2 times 2 cubed minus 0. And for space reasons, this is going to simplify to 8 pi. I may have enough room to do a little bit here. So 2 cubed, or well, 2 to the 4th is 32, divided by 4 is 8, times 3 is negative 24, plus 2 cubed is 8, times 2 is 16. No, this should be 16. Here. 2 to the 4th is 16, divided by 4 is 4, times 3 is negative 12. And 16 minus 12 is 4, and 4 times 2 is 8 pi. I had enough room. Okay. So about the x-axis. So if I'm doing x-axis, I should be delta y. Okay? So I can already tell you this is going to be first quadrant because of this stuff. Even if you don't really understand what this is going to be, this is going to be an inverse function, but we're going to look here because I know it's first quadrant. So let's get this drawn off. So 1, 2, 3, 1, 2, 3. So x is equal to 0 is here. Y is equal to 1 is here. Y is equal, oh, I already used red, sorry. Y is equal to 3. Okay, so then we have x times y is equal to 1. So if I want this in terms of y, you're probably more familiar with graphing it in terms of x. So you can graph it in terms of x, it makes no difference. So we have y is equal to 1 over x, which is that inverse graph. So I would figure out where I'm at y equals 3 and y equals 1. Well, y equals 1 is fairly self-explanatory because for y to equal 1, x has to equal 1. So I want y to equal 1. Well, 1 over 1 is 1, right? And for y to equal 3, x would have to equal 1/3. So 1/3 about right here, maybe. And it looks like this. Okay? So the area that I'm rotating is here. And I'm rotating that around the x-axis. Okay, so that means that my shell is running this way, delta y. So my thickness is determined by delta y. My radius is this distance here. So this is r. And then this distance is height. Okay, so remember, you got to visualize this spinning and making like these infinite soup cans, kind of like those dolls that all fit together, you know, and you pull it out and there's another doll and another doll and another doll. It's the same idea with like these infinite soup cans that build that solid. Okay, so that means that volume is equal to 2 pi. So remember, if we're integrating with respect to y, then our variables have to be in terms of y. So that means I'm going from 1 to 3. Okay, my radius is my distance from my axis of rotation, which is y. My height is this distance here, which is this function, the orange function, in terms of y. So this is in terms of x, so to get this same function in terms of y, you just divide by y. So x is equal to 1 over y. So I have 1 over y. And then, of course, my delta y becomes dy. So then we have 2 pi from 1 to 3. Y times 1 over y is 1 dy. Don't get overconfident here because the antiderivative of 1 is y from 1 to 3. So you have 2 pi, 3 minus 1, which is 4 pi. Okay. So use the method of cylindrical shell, the region bounded by the curve and the specified axis. So this is about y equals 2. Okay, so this is not around an axis. Now, it's a horizontal line. Okay, so I'm rotating about a horizontal line, which is like the x-axis. So that means I should be integrating with respect to y. So remember, the x-axis is a horizontal line. Y equals our horizontal line. So if I'm rotating around a horizontal line, I should be integrating with respect to y. Okay, so I know immediately if I'm rotating around y equals anything or the x-axis, then I'm integrating with respect to y, okay? So the next thing I need to figure out, now I'm going to assume I'm in quadrant 2. Yeah, I only have one function, so y greater than 0 and x is equal to 2. So I'm in quadrant 1 for sure. Okay, so I have 1, 2, 1, 2. So this is my axis of rotation. Axis of rotation. X equals 2. Oh, that was terrible. I'm so sorry. And then my function. It says y greater than 0, so that means it's bound here. So it has to be in the first quadrant. Okay, so then I would see where it's at 0. So it obviously goes through 0, 0. Let me get another color. So it obviously goes through 0, 0. And of course the next point I would figure out is how it crosses x equals 2. Not the y equals 2 because this is my axis of rotation, so I stashed. But my x equals 2, so I want x to equal 2. So that means I have 2y squared. So y is equal to 1. Now I know this would be plus or minus 1, but we're only talking about the first quadrant. So I'm not interested in what happens anywhere else. Okay, so this is my area. So remember, if I'm rotating around this line, then my cylinders run this way. Okay, delta y. So my thickness of my cylinder is determined by my delta y. Okay. So that means that my radius runs this way and my height runs this way. Okay? So that means I have volume is equal to 2 pi. Now if I'm integrating with respect to y, then my bounds have to be in respect to y. So that's 0 to 1. Now my radius is a little bit different, because remember, your radius runs from your axis of rotation to your function. So that means this distance, not this distance. So if I just put y in here, it's going to give me this distance. But that's not my radius. This is my radius. So this is just like the ones we did in the previous thing. It's not just y, it's 2 minus y. So if it had been above the axis of rotation, you would have subtracted the other direction. Okay? And then my height is between these two functions. This is a function. X equals 2 is a function. So 2 minus this distance here to this function, to the orange function, will be 2 minus 2y squared. And then, of course, delta y becomes dy. So we have 2 pi, integral from 0 to 1, and then distributive property, 4 minus 4y squared minus 2y plus 2y cubed dy. So volume equals 2 pi. I'm going to just put these in order because it makes me feel better. Negative 4y cubed over 3. Oh, that wasn't in order, was it? So 2y to the 4th over 4 minus 4y cubed over 3 minus 2y squared over 2 plus 4y from 0 to 1. So 2 pi, 1/2, 1 to the 4th, minus 4/3, 1 to the 3rd, minus 1 squared, plus 4 times 1, and then of course minus 0. So we have 2 pi. One half minus 4/3 minus 1 plus 4. 2 pi 3. And this would be, well, I'm just going to leave it 4 over 3 plus 1/2 because I'm going to have to get a common denominator anyway. So 6 be 18 over 3. 18 over 6 minus 8 over 6 plus 3 over 6. So that'll be 18 minus 8 is 10, plus 3 is 13 over 6 times 2, so 2 pi 13 over 6. The 2 and the 6 will reduce to 13 pi over 3. 13 pi over 3. Okay, we have one more. Okay, so we're about x equals 3. So x equals 3, remember, is a vertical line, and if we're doing a vertical line, then we should be doing delta x. So that's exactly what that tells me. So again, I'm in the first quadrant. So y equals 8. 1, 2, 3, 4, 5, 6, 7, 8. I'll spread this out a little bit further. 1, 2, 3. Okay, so we have x is equal to 0, which is here. Y is equal to 8, which is here. And y is equal to x cubed. So let me draw this in real quick. So x is equal to 3 is here. And this is our rotation, not one of our bounds. So if I'm in the first quadrant, I know this goes through 0, 0. So I know it goes here. So then my next one would be what makes it when y is 8. Well, that would be 2. 2 cubed is 8, right? So it looks like this. So it has this kind of shape. It's a cubic, right? So this is the area that I'm rotating this direction, which means that my cylinder runs this way. My soup can, delta x, right? Okay, so I have volume is equal to, okay, so distance from the axis of rotation is radius, and then my height runs here, okay? So 2 pi. If I'm integrating with respect to x, then my bounds have to be in terms of x, which means I go from 0 to 2, right? My radius comes next. So my radius is not just x. It's not this distance, because x would be the distance from here to here. But that's not my radius. My radius is this distance. So that's going to be 3 minus x, whatever that x value is. So like if the x value is 1, my radius would be 3 minus 1. Okay? And then my height is the distance between these functions. So it's going to be 8 minus, because 8 is on top, is above the blue function, x cubed, and then dx. So let me erase this little bit of the axis here. Okay, so I have volume is equal to 2 pi, 0 to 2, distributive property, 24 minus 3x cubed minus 8x plus x to the 4th dx. So volume is equal to 2 pi, 0 to 2. Well, we can go ahead and take the integral. So x to the 5th over 5 minus 3x to the 4th over 4 minus 4x squared. So that'll be to the 2 divided by 2. So that'll be 8 divided by 2 is 4x squared plus 24x. evaluated from 0 to 2. So we have 2 pi times 2 to the 5th over 5 minus 3 times 2 to the 4th over 4 minus 4 times 2 squared plus 24 times 2 minus 0. So 2 pi 32 over 5 minus 2 to the 4th is 16. Divided by 4 is 4 minus 12 plus 24 times 2 is 48. Where did I leave one off? Oh, I missed a term. Sorry. So this would be minus 16, and then 2 squared is 4. Did I do that wrong again? Yes, 2 squared is 4 times 3 is 12. That's the term I missed. 12 minus 16 plus 48. So I have 2 pi 32 over 5, and then we have 12 and 16 make 28, so 48 minus 28 is just 20, positive 20. So a common denominator, we get 2 pi 32 over 5, 100 over 5. So we get, I'm going to come down here, 2 pi times 132 over 5, which gives me a final answer of 164 pi over 264, sorry. Okay, 264 pi over 5. Okay, so in the packet that's uploaded from here is also the answer. This will be loaded without me talking, and then the daily grades for you to practice are also loaded. Again, the big focus is the setup. Can you do the setup? The integral is important, and you do need to practice the integrals. But the big thing is, can you draw your diagram correctly, and can you get your setup correctly? That's what I need you to understand. Okay?